Hello, everybody. Welcome to the October edition of Innovation Insights. My name is Dale Brosius. I'm the Chief Commercialization Officer for IACMI. And hopefully, wherever your fall is happening right now, the colors are changing and the temperatures as well. And as we head into this important end of the year season. Just a little bit of a reminder about IACMI. You know, we're we're organized around the theme of convene, connect, catalyze. That's our tagline, but that includes a lot of factors from networking to projects, facilities, expertise. We have co-funding available both from the Department of Energy as well as other sources, including our own membership. And we'll talk about some of those today. We've got a couple of great presenters that are presenting on projects that we have funded. Just a reminder about some upcoming events. CAMX is coming up in just a couple of weeks. We will be there in Atlanta, and I hope all of you will be as well. Last month, we had Cindy Squires on from ACMA to talk about what's coming up at CAMX. And then following that, a week after Thanksgiving is the CompositesWorld Carbon Fiber Conference in Salt Lake City. We've got Jeff Sloan today as our third speaker to give us some insights about past episodes of this and what we expect to see at carbon fiber coming up. So IACMI is pleased to partner with SAMPI, ACMA, and CompositesWorld to support these great events, and we'll be there in full force. Just a reminder, this recording is this webinar is being recorded, and it will be available on the IACMI website within the week. All of our previous episodes over the last couple of years are also available publicly to everybody. So if you missed one or you see something in this one that you think a colleague ought to take a look at, be sure to point them to the IACMI website where you can find the previous webinars. Today's lineup includes the first two speakers are resource pool projects formed out of the IACMI membership pool that were co-funded by the companies doing the projects. So we've got the report outs on the first two projects that have been funded over the last year and a half, and really looking forward to seeing those presentations, and I'm sure you will be as well. And then that will be followed by Jeff Sloan of CompositesWorld that will talk about democratization of carbon fiber and carbon fiber conference coming up. Give us a preview of that. So there is a chat function on Zoom. There is also a Q&A panel. So if you've got any questions during any of the presentations, we'll try to get to those between each speaker at the end of each speaker's presentation. And then what they can't get to in the time allotted, they will answer your questions directly in the app. So with that, I would like to invite Eric Ball, president of Orenco Composites, to come on stage and talk about the Orenco project.
Thanks, Dale.
You need to go in the slideshow.
Yeah, let's see here.
You keep mousing over it to the right of animations. Either that or go down to the bottom where the slideshow icon is.
Yeah, no,
right. Keep going over. There you go. Yeah, you're gonna need to go back to the beginning.
There we go.
There you
That look right, Dale?
Yep.
All right, thanks. So our project was really testing a new Trimer resin, which is it's manufactured by Trimer Technologies, and our company, Orenco Composites, was interested in testing this resin for infrastructure applications. Our project team was, of course, our company, Orenco Composites, Trimer Technologies, and UDRI did some testing for us, as well as Southwest Research, and of course, it's an IACMI funded project. Okay, so the goal was to test this the Trimer resin. It has mechanical properties that exceed many polyester and epoxy resins, but has significantly better FR and thermal properties. In fact, the cured resin is considered non-flammable as opposed to non-combustible. without additives, and it also meets a FAR standard there, which is a flammability test for inside of aircraft. So, like I said, we were mostly interested in testing it for infrastructure or, large structural parts. And so what we're talking about primarily are web stiffened cord panels, which I'll describe in a minute. But some of the applications would be buildings, tunnels, bridges, heliports and vertiports. In fact, we were looking at, you can see an image down there on the left of a vertiport for some of these new, the whole idea about having cabs or aircraft and take people around in big cities. Also building facades, prefabricated balconies, and a number of other applications, including the military. So what are web stiffened cord panels? These are all vacuum infused structures. You have alignment on the top and bottom, and they're connected together with a web. And there's a foam core in the middle that's typically, it can be structural, non-structural, and we tested both. But you can see this within this concept. We can change parameters, of course, the web spacing, web thickness, skin thickness, and of course the fiber architecture. That image on the right is a vacuum infused panel based on this concept. So the trimer resin can be processed with a number of different processes. We focus entirely on infusion, but it can also be, you can also use RTM, filament winding, pultrusion. One of the unique things about this resin is that it needs to be cured at a fairly high, medium temperature, 100 to 150 C. So it's not a room temperature cure. So the test schedule that we put together was we eventually wanted to get to an E119 test, which is a pretty tough test to pass. It's really a burn through test. But we start out with some simple calorimeter testing, which is E1354 to help us decide which direction to go. We also did E84, which really wasn't really necessary to determine how to get to E119, but it was interesting in terms of smoke and flame development. We also did a E119 mini test, which again was a low-cost way to help us decide the final configuration for the E119 tests. So the calorimeter test, here you can see on the left, that's kind of an example of this test, and machine there on the right. But this test measures the fire characteristics associated with heat and smoke output, and it's yeah. Let's see here. So we put together for the calorimeter test 4 different tests. We had 2 different resin trimer resins along with 2 different coatings, and we used a ceramic hybrid red coating manufactured by a company in Finland called Finister Coatings, as well as a Technofire product manufactured by Technical Fiber Products. All of these samples here were non-core. These are just solid laminates to help us determine what was going to do best looking at the E119 test. And so these are the coupons here on the picture, 4x4 samples that were run in that calorimeter test. So here's kind of a shortened summary of those tests. If you want to look at total heat release, you can see that the Technofire did a better job overall, even though it produced a little bit more smoke than the ceramic. But when we look at towards the E119 test, it's really more important to prevent temperature and burn through. So here you can see on the bottom these photographs. The second one from the left, and the fourth one where the had the Technofire, and you can see that that's an intumescent, and it really provided a good thermal break as opposed to the ceramic materials. The ceramic materials kind of broke apart. That's the first and third one, and so going forward, we felt like the Technofire was going to do a better job at protecting the laminate going into the E119 test. This is the E84 test apparatus here on the left, and I'm sure a lot of you are familiar with the E84, but it has a flame spread index and a smoke development, and those are the values we have to reach there. And in those tests, we did one with no coating and one with a Technofire on the surface. And interesting, these pictures on the bottom are just our infusion of those panels. I should back up for a second. The infusion of this material was kind of interesting. It took us a while to figure out how to do it reliably without air entrapment. It's a pretty thin resin. It's under 200 centipoise. It had some unique characteristics as opposed to polyester. We had to use some interesting films on the vacuum side or the vent side to keep it infusing properly. So there's to the test results. There on the far left is the panel with no coating, and the third one over here is the one with the Technofire on the surface. And of course, you can see after the test the burn marks there. This was kind of interesting. The laminate with no coating had a flame spread of 15, but a smoke development of only 250, whereas the Technofire had a smoke development of 400. And that's because the Technofire has to burn in order for that intumescent to work, and it added to the smoke. So if we're just looking at straight E84 results, the Trimer resin with no Technofire would perform better. But as you'll see later, that Technofire is important when we look at the E119 testing. So E84, where does it matter? If you look in the International Building Code, there's a lot of places in buildings where that really does matter. So this resin would work very well in a lot of building applications where they're occupied. This is table 803 in the International Building Code. So next we went to the E119 mini test. Again, we tested the ceramic hybrid red coating with Technofire, and we did two different cores. One was an AirX, so this is a structural core, and then we also did a polyiso core. The polyiso core was built with webs. The PET core had no webs. So this is a mini test. They're 2 foot by 2 foot panels. On the left, you can see that before the test is started, that middle one is in the middle of the test, and then at the end of the test, you can see the panels being pulled up, and you can see some of it still on fire there. So to pass this test, the temperature on the back side on the non-exposed side can't exceed a temperature rise of 250, and you can't have any passage of any flames. So here's the test results of the mini test. The ceramic red coating went 48 minutes before the temperature exceeded, and the Technofire went 51 minutes. And then the polyiso webbed core went 58 and 59. These are this was a ceramic red, and this is Technofire. Now, if you look at it over here on the pictures, you can see again where the material that had the ceramic red kind of fell apart and it really burned up. This temperatures get super hot, like up to 1800 degrees. So the Technofire provided some pretty good protection to a thermal break. So here's the E119 test. So I should back up here for a second. So after these mini tests, it was determined that it was the polyiso was a better core, and the Technofire coating was a better coating. The webs actually provided pretty good protection for the panel, because the surface that was exposed to the furnace or the temperature pretty much got destroyed in all cases, but the webs and the backside were still intact and provided good structural strength. So here, the full E119 test is pretty large, and the very severe fire test. It has to sustain an applied load during the fire test, no passes of flame or hot gases, and no openings will be developed. And there's a hose stream test at the end that can't allow water to pass through. And again, you can't exceed a 250-degree temperature rise. Here, just an example of the panels being fused. On the right are the two. We did both a floor test and a panel test. Look here in light. We had the floor panel was 12'8" by 15'8", and the wall test is 12 by 9. We went to a 4-inch thick panel. The mini tests were only 3 inches, and we did that because we wanted to achieve an hour rating, because that's a rating that the IBC is a meaningful value for a lot of standards. So here's a wall panel test. It's 12 feet wide, 9 foot tall. It's hydraulically loaded to the top at 450 pounds per foot. And on the right there, that's the inside that's going to be exposed to the furnace. Here's 59 minutes into the test. It's still, you can see it's bowing on the right-hand picture. It's bowing quite a bit, but it's still maintaining that 450-pound load. Here's after an hour, the panel frame was removed from the furnace. You can see the fire hose spraying at it there. And then here's the panel after the fire hose. So you can see that inner laminate is pretty much destroyed, but for an hour you got up to temperatures close to 2000 degrees, which is enough to actually destroy even the glass. So this panel achieved a 60-minute E119 rating, which is pretty darn significant for a composite structure. And then here's a floor test. It's similar. It was loaded at 40 pounds per square foot during the furnace test. This test, unfortunately, we built this panel in 2 pieces and bonded it together, and it failed because of the adhesive we used in the tongue and groove joint. It would have passed an hour easily had we done that joint a little bit differently, or had built the panel all in one piece. So kind of key takeaways for this: trimer resin based laminates easily will pass a class E84 without coatings or additives. It's something that we're going to be looking at is doing an NFPA 286 test, aka the room corner test. We believe it will pass very easily without any kind of coatings, and this test is planned for later this year. The Technofire intumescent fabric is not necessary for the E84 surface burn, because the trimer does a great job without any intumescent. The vacuum infused web stiffened FRP panel achieved the E119 rating in 1 hour. This is really super significant for a composite wall structure. The wall panel, like I said, would have passed easily if we were to do that again. It's predicted that this test would have failed to meet the 1 hour standard without 2 things: 1, a web stiffened core design, and B, without that Technofire intumescent fabric. It was really, it's not just the resin by itself for this E119 test, which is a very, very tough test to pass. And that's kind of a short summary. I want to thank everybody involved in the project, including Henry from Trimer, the folks at IACMI that helped support the entire project, UDRI and Southwest Research that did a lot of testing. I was at Southwest Research, and they were it was pretty fun going down there, and they're super helpful in understanding all the fire testing they've been doing for decades down there. And then the support from Technical Fiber Products for the Technofire materials. And that's about it. Thanks, Dale.
Thanks, Eric. It's always fun to go see something get blown up or, or burned up or whatever in this particular case.
Yeah.
So, we're kind of, right on time for the 20 minutes. So if folks have questions, please put them in the chat or in the Q&A and Eric will get to them on that. Eric, one of the questions, outside of buildings, I mean, would this it seems this technology also be useful for passenger ships, ferries,
Yeah.
where you have cars,
Absolutely. Depending on how structural the application is, just single skin laminates would be great. They've passed that FAR value, a FAR test for inside aircraft. I can imagine lots of applications for laminates on shelter buses, tunnels, train stations. If you want to get something more structural, like a bridge or a heliport or things like that, I think there's great advantages there too. You just have to be smart about how you put the whole thing together and look at what tests you need to pass to be applicable.
Yeah, I just remember seeing a specification out of well, I think it was Austral Ships or something. It makes a lot of car ferries. Obviously where people pull on and leave their car on and get off the other end. And the wall, there was an hour-long burn through requirement there.
Yeah.
Remember that was pretty tough. This looks like it might be similar to something like that.
Yeah. And maybe there's something out there, but I don't know of any laminate structure that would pass E119, at least not at the cost standpoint that this meets.
Yeah. Right. Okay. Great. There is a question in the Q&A, and I'll let you go into the Q&A and answer it yourself and type it in. Okay.
All right. You want me to answer that now or just do it?
Well, yeah, you can answer it now if you want. When we
the question was, are ultraviolet properties degradation data available? I don't have an answer for that. Everything we would do would have a UV coating over the top of it. So I'm not actually sure what the UV stability of the resin by itself is without a coating. I just don't know.
Okay. Yeah. I would just guess that given the other properties that it has in terms of thermal resistance, it probably would not be very UV resistant.
That would be my guess.
Not on to answer the question. So
yeah. Yeah, they can go to Trimer. I'm sure Henry from Trimer can answer that question quickly.
Yep. Okay. All right. Thanks. All right. So our next speaker is Marianne Clayton. Marianne's a R&D engineer with IsoTruss, and you may be familiar with IsoTruss from some of their communications towers, but we set them out to work on something entirely different, and I think you'll find it very interesting. So Marianne, welcome.
Thanks, Dale. So I'm Marianne from IsoTruss, super excited to be here, and thanks to IACMI for inviting me to be here and also for the funding for this project. Well, we were looking at using lattice IsoTruss structures in wind turbine applications. Here's my outline for today, and this picture is a preview of our demonstration piece we're really excited about. And that's kind of the end result of the project. And I want to tell you the story of how we got to this particular design. So I'll start with the problem, the design, and then talk about this piece and then conclusions that we learned from the project. Our project was looking at wind turbine towers. So these are really big towers. And we, like Dale said, IsoTruss, we do telecom towers, but can we use the same technology and apply it at a larger scale? And then we wanted to demonstrate that this was feasible with a demonstration piece. And the purpose here is to create infrastructure for wind turbines that's easier to install and corrosion resistant. So it will be longer lasting and then still have the same mechanical performance as current solutions. So a little bit about IsoTruss. These are 3 pictures of IsoTruss towers that have been deployed. The picture on the left is an installation at about 11,000 feet elevation in Wyoming for the Bureau of Land Management. And this is important for them. It's a communications tower to contact their field agents that are out in the middle of nowhere and also to coordinate efforts with wildland fire management. And the issue is that this location is only available for a few months in the year, and the only way to get to the top is a dirt road. So not possible to get anything too heavy or a crane or big equipment. And what was feasible was only a small steel tower, and it kept breaking due to high winds and snow. So they approached us for a different kind of solution. This tower you see here was delivered to the site on a trailer with just a pickup truck and then installed by hand. And we're really happy to report that it withstood a really heavy snowfall winter last year, and the tower was still functional by the end of the winter, which is really exciting. These other two towers here are installations in the Philippines, which have really high corrosion issues because of saltwater exposure, and then also high winds due to typhoons. And in particular, the picture in the middle has withstood several typhoons at this point and is still functional, which is really exciting. So how do we take this technology for these smaller scale towers and make it for a wind turbine? So first I'll talk about the tower design. We focused on 3 challenges of steel towers for wind turbines. So first, transportation. You have really large components that are heavy, and so you need specialized equipment to transport and also specialized routes. You can't go under overpasses, you can't make tight turns, and that makes it challenging to get the components from where they're manufactured to the installation site. Second, installation is expensive and time consuming because of large heavy pieces that need big equipment to move into place. And then third, corrosion can be an issue with steel, right? Especially as more wind moves to offshore applications. It would be nice to just have that not be an issue. So for this project, we used an NREL 5 megawatt reference turbine, and you can see the specifications for the turbine itself on the left. And then we put this information into the Wisdom software to get the specifications for the tower. So this tower is 88 meters high. It's tapered, so 6 meters at the bottom, 4 meters at the top. And you can see there the mass 256,000 kilograms. The first design was to create the same monopole design tapered tower out of carbon fiber, a solid carbon fiber piece, and then also out of IsoTruss. And these were designed to match EA, EI, and GJ of the steel tower. Here are the dimensions from that analysis. So the steel tower is 6 meters at the base. The solid composite is 14 meters at the base, and the IsoTruss tower is 30 meters at the base, which makes sense. You're working with material that has different stiffness properties. So to match stiffness needs a bigger base. Significantly though, the composite solutions are a lot lighter, and the weight, you can see that the weight's reduced by about half for the composite solutions versus the steel tower. So going back to those 3 problems with steel towers, transportation isn't really helped. They're lighter, but they're even larger components. So all the issues with needing specialized equipment to transport and specialized routes to get there aren't actually helped. Installation, it's difficult to say if it's better or not because the components are lighter, but they're also larger. So maybe it evens out and not a clear advantage there. And then of course, composites are more corrosion resistant. So there is a benefit there. So rather than just trying to replicate the steel design and just change the material, we decided to take a different approach and look at a different design that takes better advantage of the unique properties of composites. And that's this you see here, a modular IsoTruss tower is what we called it. So this picture on the right, each line is a 20-foot IsoTruss section that are shipped just as individual sections to the site and then assembled there. And the key to this design is to have joints that are effective both structurally and also for installation to be easy and in a timely manner. And the large benefit here is to not need as much specialized equipment to get the pieces there because it's just shipped in building blocks and then assembled on site. So joints, what do you do to connect the sections? Here's a couple pictures of other IsoTruss joint applications. So on the top, this is an IsoTruss bike and it uses solid composite connections. This is assembled in a manufacturing facility and then shipped fully as one piece. And then on the bottom is a close-up of a tower joint, which has flanges built in to the IsoTruss sections that allow these plates and bolts to connect the tower pieces together. And for this one, we went with a design similar to the towers with bolted connections so that they could be easily assembled on site. So here are those same dimensions for the modular IsoTruss tower versus those other designs that I showed earlier. And the modular IsoTruss design can match the dimensions of the steel. So 6 meters diameter at the base, 4 meters at the top, but significantly it weighs much, much less. And this table shows all of those numbers as a factor of steel. So the solid composite has a base diameter 2.5 times that of steel, the IsoTruss 5 times that of steel, and modular IsoTruss the same as steel. And you can see on the bottom the weight that the modular IsoTruss solution is only 1/10 that of steel. So if we look back at those 3 challenges to steel towers, transportation is a lot easier. You can put the IsoTruss sections in a typical shipping container on the back of a semi truck to get it to the right place. Installation is easier. You're just moving small, lightweight pieces around, and then you get the same benefit of corrosion by switching to composites. So that leads us to the demonstration piece. We wanted to show what this looks like in real life. So we took structural IsoTruss components, and then we have non-structural 3D printed joints just as concepts for what this might look like. And we designed it specifically for easy assembly and disassembly so that it could be shipped to different places. Here's pictures of the completed thing. And it is meant to look like the modular IsoTruss solution where you have building blocks of IsoTruss sections that are put together for the full assembly. These models show detail of the joints themselves used in the demonstration piece. So they are curved to fit around the vertical IsoTruss sections, and then these cylinders on the side allow the diagonal IsoTruss pieces to fit on, and then they're secured with brackets. And then these pictures show a little closer view of both IsoTruss sections and the joints that are used in the demonstration piece. So we're really excited about this piece, and it will be at the IACMI booth at CAMX. So if you're there, please stop by and take a look at it. So conclusions. I think this project shows, like many other things, that composites have promise in infrastructure applications, but it's important to use designs that take advantage of the unique properties of composites rather than just trying to copycat steel solutions. And I think where composites really shine in infrastructure applications are where they can have installation savings, both in time and cost, and then also corrosion resistance. And we've also learned some important future research opportunities from this project. So material costs are one of the highest components of the product. And so doing things to reduce material costs, like different manufacturing methods, switching from pre-preg to infusion or other wet winding, different ways to reduce material costs, or potentially even switching kinds of fiber, has a big influence on the cost. And this is important because we've seen customers are generally unwilling to pay a premium for products, even when they have better features and longer lifetime guarantees in infrastructure. They need to match cost with steel, and then the added lifetime benefits can put people over the edge for adoption. Manufacturing scale is important because you're competing with commoditized materials. So a hand layup process isn't going to cut it. It needs to be something that can have low manufacturing costs and be at a scale that can compete. And then joints, if having effective joints that are easy to install and that work effectively could open up numerous opportunities for IsoTruss and other infrastructure applications. So with that, I want to say thanks to IACMI and also Steve Nolet, who was our advisor for this project. And thank you for letting me come today.
Thank you, Marianne. Just pointing out, Steve Nolet is with TPI Composites, who is obviously in the wind industry, and so this was a project that arose out of our wind technology working group that showed an interest in what this might look like. And so obviously there's still more research to be done, more analysis, but we've got a couple of questions. We've got one in chat, and I imagine this was probably not your bailiwick, but at least we'll bring it up. Is does the IsoTruss create an aero disturbance for the downstream blade in the farm?
Yeah, that is not a question that we looked at in this project, but definitely something to think about. Generally, the wind resistance of IsoTruss is less than a solid tower, so it would be definitely interesting to look at how that interacts with the blades.
Yeah, how that models in a large farm, for example.
Exactly. Yeah.
Okay. So one coming from the Q&A panel, what's the estimated life expectancy for the modular towers?
I think what will wear out on the tower is going to be the bolts. That's the only piece that would be subject to corrosion. So I think, and lifetime is always something that's difficult to answer with composites. But the longest IsoTruss tower has been up for 30 years and has no indication of anything wearing out. So lifetime is promising.
Yeah. Okay. The joints themselves, what would you envision there? Would those probably be steel joints in a full scale tower?
I think, well, for this project, we designed a composite joint section that you could fit in between the IsoTruss sections that's just connected with steel plates and bolts to try to minimize the amount of steel that's in the solution.
Okay. Okay, more questions, and we have time to get to them. How would the tower be attached to the ground?
IsoTruss towers just use the same foundation as typical steel towers. So I'm assuming for this, we didn't look at that specifically in this project, but foundation connections have always been the same as steel towers.
Okay. How would you deal with UV resistance on the towers? Would you have to put a UV resistant coating on?
I think, yeah, the best way to do that is just like what Eric was saying earlier with coating, like is done in other composite applications and infrastructure.
Yeah, obviously there are UV absorbers that could possibly put into the resin, but
Yeah.
Paint anyway. Steel tower has to be painted, of course. Yeah. Okay. And glad to see Ignace Verpost joining us from Europe. Exciting concept. Some concern about the many or rather complex metallic joints, which could be prone to stress concentrations and fatigue. So maybe more of just a comment, but one you might want to address.
Yeah, appreciate that. Thank you.
Okay. Boy, another this is great. I'm glad to see Clem Heil on as well. Is there an automated manufacturing process already in place for these IsoTruss elements?
Yeah, that's a great question. So IsoTruss grew out of university research, and at the university level, the automated concept was braiding. We haven't done that commercially, but we are doing filament winding. Automated filament winding is our path, and we'll see where we go in the future. We're kind of open to different ideas, and we'll see what happens.
Okay. As we've cleared the questions, if there are more, please put them in the chat or in the Q&A, and Marianne will monitor that and try to get those answered in the next 20 minutes. All right. Thank you very much, Marianne.
Thank you.
All right. And we've come to final speaker, and that is Jeff Sloan. Probably needs no introduction, but Jeff has been elevated to brand vice president for CompositesWorld, where he used to be the editor of CompositesWorld. And, most of you have seen Jeff present at various things over the years. And we invited him to come in because at the end of November is the CompositesWorld Carbon Fiber Conference, which is a great annual event this year in Salt Lake. So, Jeff, I'll let you take it from here.
Great. Thank you, Dale. Appreciate it. And hello, everybody. Again, my name is Jeff Sloan. I'm brand VP. That's my new title. Technically publisher of CompositesWorld. And as Dale noted, I used to be the editor-in-chief. So thanks to IACMI for inviting me to present at this Innovation Insights event today. So as Dale mentioned, a lot of what I'm about to present are thoughts that I had as we started to develop content for the Carbon Fiber Conference, which is coming up at the end of November. So I'll talk about that briefly at the end, but wanted to explore some of the ideas that will be expressed and shared at the conference to kind of give a sense for where we see the carbon fiber manufacturing industry right now and where it might be headed over the next few years. All right, so I hope most of you, or at least have heard of CompositesWorld. We're a B2B trade magazine that serves the global composites manufacturing industry. I say magazine, we're actually a brand because we provide a number of products for this market, depending upon how you like to receive your information. We're very strong and well-known editorial team, now led by Editor-in-Chief Scott Francis. Some other names here you probably recognize, like Ginger Gardner and Hannah Mason and Grayson Karras. So, proud of this brand, feel like we do a good job of serving the entire industry, focused on design, tooling, fabrication, and finishing, and serving all the major end markets: aerospace, automotive, marine, consumer, etc. So that's us. That's our place in the market, and appreciate you consuming us and supporting us. All right, so what I want to talk about today, these 7 things. I want to look at the traditional value proposition for carbon fiber, which I think is pretty straightforward. Where carbon fiber has been, what I see as the current state of the industry, sustainability challenges, new markets, the commoditization of carbon fiber. I think Dale called it democratization, which I think is suitable as well. And then I'll talk briefly about how the Carbon Fiber Conference will address some of these challenges and where we are today. All right, the traditional value proposition, you can see here that it's pretty straightforward, and the repetitive use of low weight, I think, sends a pretty strong signal that this is typically how we argue in favor of use of carbon fiber composites or composites in general. Combination of weight savings with really good mechanical properties is physical performance, combined with corrosion resistance, which has already been talked about here today, and of course durability. And all of this combines to provide, create some really compelling benefits for manufacturers. Fuel efficiency is the big one. Extended product life, and then you get knock-on benefits. If you're reducing weight in a structure, it allows you to reduce weight in other components of a structure or a part, and then you get ultimately net savings. And that's been the argument that the composites industry has made to prospective customers, throughout the life of this material. And none of that's new, and I'm sure that all of us are very familiar with that. So this is my assessment of where the industry has been over the last, say 20, let's just say 30 to 40 years. My argument is that through the 80s and 90s, through the 80s and 90s, composites were primarily a displacer of legacy materials. So if you think about the use of wood or concrete or titanium or steel or aluminum, composites were usually positioned as a way to improve an existing application by displacing a legacy material. And this gave birth to black aluminum. And this is primarily how composites, quote, earned their way onto applications or into markets. A lot of that changed in the early 2000s when Boeing with the 787 and Airbus with the A350 decided to use carbon fiber in primary aerostructures for the first time in a major commercial aircraft. This was enabled primarily through advances in automation, automated tape laying, which you can see there on the A350 lower wing skin, and the 787, which you can see as well there on the forward fuselage. These technologies allowed fabrication of large structures more efficiently and effectively in a way that make it make sense for Boeing and Airbus to use on those aircraft, which increased the efficiency of the aircraft, reduced weight, fuel savings, and then all those knock-on benefits that I mentioned earlier. We also saw this happen with the F-22 and the F-35. The F-22, of course, is no longer being produced, but the F-35 is. And then in the 2010s, we started to see carbon fiber work its way into wind blade spar caps. As wind blades get longer, you need these pultruded spar caps to provide the stiffness that the blades need. And then we also saw in the 2010s the BMW i3 and i8, which made use of carbon fiber in very new and interesting ways. At the time, I think we all kind of thought and hoped that this might be a harbinger of things to come for the automotive industry. It turned out that the i3 and the i8 were more unicorns and interesting, but not sustainable in terms of carbon fiber application. But still, a lot of activity over the last, particularly last, I'd say 15 years in terms of how carbon fiber is being applied, penetration in different markets and structures. But throughout this, we still had challenges. There was a fair amount of immaturity in carbon fiber supply. There was variability in the supply. And there's a lot of high capex with carbon fiber manufacturing, which made it difficult for suppliers to respond to market signals for demand. And barriers to entry were high as well. And then, of course, we've got fabrication immaturity, typically the use of hand layup, which of course is still used today, but typically hand layup or spray up. Use of manual labor has been a challenge. Cycle times have been a challenge. Material cost has been a challenge. And all of those things still exist today to some extent, but getting over some of those hurdles has been an ongoing challenge for the industry. All right, so where are we today? Carbon fiber is very well penetrated into some markets that have made really good use of this material. Aerospace is the most valuable in terms of carbon fiber use. But in terms of volume, wind is the largest and largest by far. And wind over the next 10 years is expected to grow even more. I think by 2028, the expectation is that the use of carbon fiber in the wind industry will potentially double. And so we're seeing a lot of material going into these markets. I've listed here some of the aircraft programs or aerospace programs that are using carbon fiber significantly. The 787 and the A350, of course, we've talked about the F-35. The LEAP engine is on the Airbus A320 and the Boeing 737. The 777X has the very large carbon fiber wings. So a lot of programs, very high profile, well-known programs are using carbon fiber. There continues to be modest automotive penetration by carbon fiber. There's a fair amount going on with battery enclosure systems. I've got a photo there of the Tasian system, which uses a fair amount of fiber, but also a lot of glass fiber going into that application. Sporting goods continues to be a strong market for carbon fiber. You think about golf club shafts and tennis rackets and hockey sticks. Formula One is very high profile and kind of sexy use of carbon fiber. And then, of course, pultruded wind blade spar caps continue to be a strong application. But there's a big but here. There's no new aircraft program on the horizon. And I think this is somewhat disconcerting to the aerospace supply chain. Boeing is in a relatively weak competitive position right now and has made very clear over the last few months that there are no plans to announce a new single-aisle aircraft program before 2030. And whether you agree with that or not, and I don't, that's the way it is. Of course, that may change. If Boeing leadership changes, there may be a change in strategy, but that's the situation right now. Airbus, for its part, is very happy where it is. It's in a very strong position. Doesn't need to do anything differently. But the result is that the supply chain, Aero Composites supply chain, is kind of in this holding pattern until we have some stronger sense about where things are going on the commercial aerospace side. But that said, there are opportunities in new markets and new applications, which I'll talk about in a second. But right now, the aerospace supply chain is definitely waiting for a new aircraft program and eager to apply some new materials and technologies there. All right, so the sustainability challenge / opportunity, because we don't talk about problems, we talk about opportunities, and that's what this is. One of the byproducts of COVID, as I think we all know, has been a renewed focus on sustainability. And this is at the regulatory government level and at the business level. And so what we're seeing, of course, is that major OEMs are establishing sustainability goals, and then they expect their supply chain to get in line with those goals and to meet those goals. And then we're seeing as well on the regulatory side, some similar requirements being made, particularly in Europe, but some here in the US as well. One of the byproducts of that is that there's been some new scrutiny placed on carbon fiber manufacturing. So as I noted earlier, we've always argued that we save weight, and that's the big benefit, and that's good, of course, and that typically has been enough. I just don't think it's enough anymore. Carbon fiber manufacturing is a very high energy process, and it uses a petroleum-based precursor, polyacrylonitrile, which makes the carbon footprint for carbon fiber manufacturing not so good. And so there's a lot of effort now to decarbonize carbon fiber production, development of bio-based precursors, pan precursors that use biomaterials, and also attempts to get energy out of the process. So there's an opportunity here as well to rethink and recalculate what the carbon fiber value proposition is. And I think based on signals that we're seeing in the market, that the real benefit over time of a carbon fiber structure is its lifespan. And the longer it can be in service, the better job it does of offsetting the penalties you pay up front for that high carbon footprint. So I think we'll see over the next few years more data come out on this. But right now, this is a significant challenge for the industry. All right, so new markets. There's in response to this decarbonization, this global decarbonization strategy, we're seeing a lot of activity that is, and as I said in the previous slide, on the one hand, putting new scrutiny on carbon fiber and its application, but on the other, increasing its use in certain applications. And probably the biggest one here is the hydrogen economy. And when we talk about hydrogen, we're talking about applying hydrogen, particularly in fuel cells for transportation. So trucks, trains, buses, and some personal vehicles. But you have to store the hydrogen, and the best way to store hydrogen is in carbon fiber pressure vessels. So that's a big opportunity. Advanced air mobility is coming with the first aircraft for this space to come into service in 2025 and 2026. There is a lot of uncertainty about how this industry will grow, how quickly, and where. But I think it is safe to say it will be born, and it does use a lot of carbon fiber composites. These aircraft are all battery-powered electric aircraft, and so they absolutely need composites to reduce weight and make them viable as a mobility technology. The private space race is another one. I've got a photo here of a fuel tank from the Firefly Aerospace structure based on a story that we did recently. And then continued use of carbon fiber and wind energy. And then one of the big question marks on the horizon is the Chinese carbon fiber manufacturing industry, which I'll talk about in a couple of slides. But manufacturing of carbon fiber in China has traditionally been relatively low volume, but there's been a lot of investment by the Chinese government there, and so we're seeing a lot of activity. So one of the byproducts of all this, my observation is that carbon fiber has become an enabling material. And as I argued earlier, where in the past, carbon fiber was a replacement material, making it an option in a lot of applications. My argument is that it's becoming the only material option for a number of markets and applications. Hydrogen is one of them. You cannot produce the kind of pressure vessels that are needed for the hydrogen economy without a lot of carbon fiber. You cannot manufacture aircraft for advanced air mobility without carbon fiber. The new space segment absolutely needs carbon fiber. And then we cannot build the kind of wind turbine blades that we need without carbon fiber. And there are very few, if no other alternate materials available for this. And so carbon fiber in a way is feeling the kind of pressure that a commodity material often feels. And so it's leading to some commoditization or democratization of the material, which I'll talk about in a second. But it's also putting pressure on carbon fiber suppliers to change their behavior and to rethink how they produce their material. On the fabrication side, there's a lot of pressure now to produce structures with more automation, less labor, higher volumes, using better process control. This is driven a lot, particularly by the aerospace, the advanced air mobility industry, which is looking at producing a lot of aircraft, but at aerospace quality. And that's a combination we're not used to. And we're going to have to get used to and produce the manufacturing systems to meet that expectation. All right, so carbon fiber is a commodity. So typically, these first few bullets are describing carbon fiber manufacture as it is today. It's a very highly specialized advanced material that uses a specialized precursor with specialized formulas, and those formulas are designed to produce material with properties suited for specific applications. And so the photo you're seeing here are the buildings at the Hexcel facility, manufacturing facility in Salt Lake City. Each one of those lines produces fiber for a specific application or produces fiber of properties designed for specific applications. And so there's not a ton of flexibility in carbon fiber manufacture when it comes to material properties. In addition, as I noted earlier, the CapEx here is very high. There's a long lead time for expansion, usually about 2 years from the time of announcement to the time of production. And then it's a very contract-driven industry, meaning that a lot of carbon fiber suppliers like Hexcel don't like to produce fiber unless they have a contract in place for it to go to a particular customer. And so without those contracts in place, it makes it difficult for a carbon fiber manufacturer to justify the kind of expansion that a market might need. All of these are high barriers to entry. But as I said earlier, I think this is changing. Because of the dynamics of these new markets like hydrogen, like advanced air mobility and others, it's putting unusual demand on carbon fiber suppliers to be more responsive and more adaptive. I think it's also creating an environment where we could see new suppliers into this market, folks producing carbon fiber who we haven't seen in the past. And then, of course, there's always the Chinese issue. The Chinese, as I noted, are producing more and more carbon fiber. The quality from what we hear is not quite on par with what you can get in the US and in Western Europe, but it is improving and there's a lot of investment there. Most of the carbon fiber in China is being consumed in China right now, but that could change. And if that does change and carbon fiber is sold outside of China, it's not hard to see that there could be a lot of pressure and changes imposed on the supply of carbon fiber globally. So all of this will be addressed, I hope, in some way or another at the Carbon Fiber Conference, which is coming up at the end of November. Excuse me. This is if you're not familiar with it, the carbon fiber is in its 26th year. It's hosted by CompositesWorld. And this is a 3-day event. It's got a 1-day pre-conference seminar and then a 2-day regular conference. This is a business and technical conference with a lot of networking opportunities. And so we start on November 28th, and that's the pre-conference. And there we'll be looking at carbon fiber use in wind, aerospace, and then a look at what's happening in China. And we're going to finish with our annual look at global carbon fiber supply and demand, which is always very popular. And then on the first day of the regular conference, that's the 29th, we're going to be looking at sustainability, the hydrogen economy, commoditization, and then carbon fiber use and 3D printing, among other topics. And then on the final day, we're going to start with a panel. And that panel is going to be assessing what happened with the Titan submersible, which was produced by OceanGate. And if you recall, the Titan imploded during a deep dive in the North Atlantic over the summer. Lots of questions raised about the manufacture of the Titan, materials use, but the hull on the Titan was made with carbon fiber. And we're going to have a panel of experts looking at the use of composites and submersibles and what is feasible, what is reasonable, and what kind of design considerations need to be made there. And we'll be getting into recycling as well. We're looking at carbon fiber use in high rate electronics, and then, of course, advanced air mobility. So this is a good event. It's a fun event. We put a lot of work into developing content for this. I encourage anybody who's interested to please join us. I've got the URL for the conference there. If you want to learn more, look at the entire agenda of speakers we have planned. I think you'll find it of interest. So Again, thank you to IACMI for supporting us, supporting CW, supporting the Carbon Fiber Conference. And thank you for letting me speak today. I appreciate it. I'm open to any questions that anyone might have right now.
Thanks, Jeff. Appreciate that. We've kind of hit the end of the hour, maybe even a couple over. We've lost a few folks, but always great to get the insights about especially about the markets that absolutely have to depend on carbon fiber in order to be successful. And that number keeps growing. So, So Kim's put the URL in the chat for us. Don't see any particular questions, but I'm looking forward to be there. It's the 26th year. I personally have probably made somewhere around the 20
Pretty close.
Yeah, so it's a place, it's a conference I've always found to be exceptionally rewarding to both present at and be in the audience at. So I'm looking forward to
seeing you there, and hope we'll see others there as well.
Okay, so we'll see everybody else in a couple of weeks at CAMEX, and
that's right, we'll be there
CAMEX
too.
And the beautiful fall weather and the rest of your week. Thanks again for attending today, and we'll see you in November for the next edition of Innovation Insights. Thanks all.